Hello, one more video for today. In this video, I want to talk about more of a historical context of when these foundations of mathematics were being laid out. So let's jump right into that. Okay. So I want to talk about a particular book or a set of books called Principia Mathematica. So this is let's see, from 1910 to 1913 or so, this series of very thick books um, done by Alfred Whitehead and Bertrand Russell. You might have heard of these names. They're both very famous mathematicians slash philosophers. Um, so these are the people who kind of try to lay out all of mathematics into rules and symbols and rules on how to manipulate these symbols to create all of mathematics from the ground up. So what was happening at this time in the late 1900s is that mathematicians were doing their own thing in different fields, and different groups of mathematicians had different degree of how strict they had to be for some argument to count as a proof. And there's been several instances where they have discovered, oh, there's a mistake in this result, this theorem, but there's actually no error in the proof. Well, the error is in the theorem that's used elsewhere, and it became apparent that we needed like a common starting ground that all the mathematicians could agree on. And this movement was set forth by David Hilbert in a really famous, like an international speech at 1900. Anyways, so mathematicians are trying to work hard and trying to see if we can make mathematics develop from something that's very basic. Now, let me kind of show you what this book looks like. It's very weird. Okay, so if you Google Principia Mathematica and then Internet Archive, you could see here, you could come to this page and you can actually kind of flip through what the book looks like. So let's kind of jump into what the book looks like. So this might look like a regular math text, but if you kind of get deeper in there, maybe I'll just jump to a couple hundred pages. You'll start to see how messy this book becomes. Look at that page. It's crazy. This looks like one of those when printer gets an error and it starts printing a garbage. Right. So all of these symbols are meant to be something. Stop looking at that. Yeah, it's unreadable, right? Anyways, that's what Principia Mathematica looks like. And it had two main goals, right? So one was to prove that mathematics is consistent. So what consistency means here, in logic, something is consistent if the logical system does not contain any inherent contradiction. So it would be very disappointing if mathematics kind of contradicted itself. In fact, in any logical system where you can create contradiction from nothing, um, you could prove anything in that system. So it becomes uninteresting as soon as you can find a contradiction within that system. The second goal was much more ambitious goal, is to show that mathematics is complete. Here, completeness means that anything that's true is somehow provable. So any true statement is provable. So if you can write down some fact about like numbers that is true, then maybe there's a way to come up with that proof. So the axioms were strong enough to show what you want, complete, but no stronger than that. If by stronger I mean it doesn't start proving things that are false. So these were the two goals, and they wanted to fit all of mathematics in a common starting ground. And it's kind of inspired by Russell's paradox here. So this is a really interesting paradox. So here's Russell's set R. So try to understand what this is saying. So R is a set where it contains all of the sets where the set does not contain itself. Okay, so any set that does not have itself as a member should belong to the set R. If you think about this for a little while, you realize that this will create an inherent contradiction, right? Because if that set R contained itself, then it should not contain itself because that's the rule for being in the set. But if it does not contain itself, then it should be contained in there. So if you try to make sense of the set, and if you can somehow create a set that looks like this, then you have a contradiction within the system, right? Because you have something that belongs to a set and not belong to a set at the same time, and that should not be possible. So that's Russell's paradox, and Principia Mathematica does get around this paradox and successfully develop some version of the foundation of mathematics. It's not the modern version that's used today, but close enough. By the way, if you're wondering how they were able to get around it, you have to know a little bit more set theory. But there is one of the axioms that kind of eliminate. You can't really build a set that contains itself under that axiom. So one of the axioms kind of eliminates this in a roundabout way. Okay. So in some sense, it was good because it brought mathematics to a common ground. But there's a couple takeaways that I want you to have here. It's not the greatest text in the world. This book is unreadable. Like, this is not, it's a nice book as a historical fact that it was written. But if you sat there and trying to read this, it is impossible. I think this book only existed in the author's head for the 3 or 4 years it took them to write that book. They originally planned to publish 4 volumes, but they kind of ran out of steam and they could not finish it. the part of what makes it unreadable is that it's not written in English sentences. Like a lot of it is just symbols and lines of symbols. It kind of is a reminiscent of maybe like a computer program that's in assembly code or something. Um, it is kind of written for computers, right? So maybe it has all the ambiguity taken out, but strings of symbols is not the way to write or read mathematics. So that should be one of the takeaways, is that um, they couldn't even continue writing it. It's really not readable text. Um, the number two takeaway um, is that it was unsuccessful as far as the ultimate goal. So when I say ultimate goal, I mean these two goals. The book was not able to prove that the mathematics were consistent. It was not able to prove that mathematics is complete. Um, and we're going to talk more on that later, but it turns out both of these two goals are unachievable. Mathematics cannot prove itself to be consistent, and there are some statements in mathematics that are true, but there's no proofs available. So we'll get to that later. But yeah, so that's kind of sad as far as that goal goes. But I think actually that makes mathematics more interesting. That it keeps mathematicians like me have a job, right? So if it was complete and we can figure out some kind of formula to prove everything, then we no longer need mathematicians in some sense. Um, yeah, so I think that's where I'll stop here today. And on Thursday, we will start chapter 2. Okay.